So while we're setting, maybe I can present the team. So I'm Valentin. I've been leading the development of MAPIE for the last year or so. And I'm handing off that role to Geoffray, who's here with me. We're both working at Capgemini Invent. And we're very pleased to have welcomed Adrien to the team. And so thanks to P16, Adrien will help us develop and grow the project. And so today we are going, oh, okay, let's get this. Yeah. Today we are going to first understand why it's important to measure uncertainty in machine learning or data science context, because you've guessed MAPIE will help you do so. Then, of course, we'll talk about MAPIE and we'll conclude about the roadmap. So, why quantifying uncertainty? Well, we tend to rely more and more on machine learning models, even in verticals that are critical, for example, healthcare or warfare or transportation with autonomous vehicles, for example. But not everyone can afford to fail in order to gather more data, like SpaceX does, for example. And sometimes we want to try to be right the first time. And so to do so, you need to provide the business or the users of your models more context about a model prediction. And that context can be, that context can take several forms, but in the context of uncertainty quantification, that context can be, for example, a confidence level on a specific prediction, so that the business can take an informed decision. And so there are, of course, many methods to perform uncertainty quantification. Here we like conformal prediction and the more general framework of risk control, because, well, it also has drawbacks, of course, but it's interesting because it's model agnostic, so we can use it in a lot of different use cases, and also it's mathematically grounded, so we provide statistical guarantees about what we say. And that's actually how MAPIE was created, because we needed a good library that implements conformal prediction. And so two very simple examples to introduce you to how that works. So first, let's take a regression task. So here we are trying to infer the age of someone given their portrait. And a classical machine learning model will output a number, right? And thanks to conformal prediction, we will give you a prediction interval associated with a confidence level. Of course, there is a trade-off. So the more confident you want to be, the wider the interval will be. So in that example, if we wanted, let's say, a 99% confidence interval, maybe the interval would have been like 15 to 35. So there's always a trade-off, of course. And in classification, we're not talking about interval, but rather set. And here we try to guess the species given an animal picture. And here even a human will probably hesitate between two classes. So we can see that it's pretty interesting to be able to output prediction sets instead of just prediction points. And I will let the floor to Adrien.
Okay, so now I'm going to introduce a little bit about MAPIE. So MAPIE is a library that implements uncertainty quantification methods, so mostly conformal prediction. And I think it was the first library implementing conformal prediction method. And if we compare to different libraries that are more recent, We have more GitHub stars, so which it's nice. It's like a vanity metric we talked earlier. And the users of MAPIE are located around the world, so it's not only in France. So besides the code of MAPIE, there is also an extensive documentation, some scientific publications, blog articles, and educational resources. So it's aimed at users to like easily understand what MAPIE does and how to use it. So MAPIE can be used to solve different kind of problems. For instance, regression problems, where we predict a value from data. And MAPIE can be used to compute intervals around the value. Similarly for time series, but also classification, where now you can only, instead of having only one class predicted, you can have a set of classes when the model is uncertain. Like, for instance, here in between two clouds of points, maybe the prediction is uncertain and contains multiple classes. There is also risk control, which is a generalization of conformal prediction, where now we can use, like we can optimize any risk function and have some statistical guarantees on it. So for instance, if we have a binary classifier, we can compute some guarantees on a given precision level. So if we want our classifier to only have above 80% of precision, then we can use risk control methods to get it. And there is also other stuff like a little bit of calibration, etc. And one thing that is coming soon is to use risk control for LLM use cases, where, for instance, if we take a binary classifier on top of an LLM that can predict, for instance, hallucination or toxicity, then we can apply risk control methods to guarantee the behavior of this binary classifier. So we can have some guarantees on the binary classifier on top of the LLM. So now let's see the intuition between how conformal prediction works, so like the core of MAPIE. So we start with a fitted model. Here it's a girl that learned how to shoot arrows. And what we want here is to evaluate her performance on a new setting. Like we ask her to shoot some arrows on this target. So then we can compare the result, like the real performance compared to the prediction. So the prediction was to always hit the center, but in practice, it's not always in the center. And on this data, we can see that 90% of the arrows were in a blue circle here. Sorry. And we can use this information at test time, where when the girl makes the prediction that she will hit the middle of the arrow, from the conformalization step, we know that actually there is 90% chance that the arrow will hit an interval around the prediction. So we can use this information to trust or not the model prediction. So for instance, here, if the prediction interval includes the head of the guy, maybe we should not use this prediction. So to see how it works in MAPIE, we start with a trained model, for instance with a scikit-learn, and use it to initialize a MAPIE object. And then we can call the conformalize function from MAPIE to compute to assess the model behavior on new data, which is not the training data, it's called conformization data. And then at test time, MAPIE can compute some intervals around the prediction or sets in the case of classification. So translated into code, it's quite simple. So we just have a few lines to define our model and train it on some training data. Then we can define some hyperparameter values like the confidence level we want associated with the intervals or the sets. And construct the MAPIE object and just call the conformalize function. And then at test time, we can use the predict functions from MAPIE to not only have the point prediction, the original prediction, but also the interval around the prediction or the set in the case of classification. And now to Geoffray.
Yeah, so I will present you what is coming next. Here is the present. So we released recently MAPIE v1. It was a major refactoring of the interface with the user to help the user have an easier way to use MAPIE. And we released recently the version 1.1, which included for the first time some function for risk control for binary classification. And this is something we are still working on. We want to further develop onto this feature, notably to enable controlling of some risk with LLM-based systems. One major drawback that is always raised when we talk about conformal prediction is the idea that our guarantees are only on a marginal condition. So we are, let's say, we want to be sure 99% of the time it will be on the whole population of interest, and we have no guarantee on subpopulation. So the idea would be to include some conditional coverage functionalities to alleviate this drawback. And we still receive some suggestions from the community and some feedback from users. So we still integrate them as quickly as we can. Yeah, so here is the kind of MAPIE ecosystem. So at the top, you have the core team. So it's a lot of people, mainly from Capgemini. And on the bottom left, you have all our partners. So we have industrial partners and some institutions like Université Paris-Saclay, Confiance.ai. And we have also a lot of contributors coming from the community of open source Python. And so it's a big family to develop this tool. And I will finish with some example using MAPIE in production. So this is actually what MAPIE is used for. On the top left, you have an example where we want to do some quality control on some batteries. The idea is we produce a battery, we took a lot of parameters from the production, and we are able to have some estimation of quality indicator. The idea is the lesser the indicator is, the better it is. And we don't want to sell batteries above a certain threshold. So by using the conformal prediction with MAPIE, we can be sure, that we exclude the very low quality battery. For some batteries, we are really uncertain, so they will be sold as lower quality batteries. And for some batteries, we are really sure we meet our quality criterion, so we will sell them as high quality batteries. Below, you have an example for time series. This is an example of price prediction, where you have the Warunic trend here making the price go up. And here you have, I think it's the COVID, I'm not sure, making the price go down. And the main thing we want to highlight is before this event, we have a really tight confidence interval around our prediction. And when things get really messy, we have a very wider confidence interval. So we are able to adapt to what the model is encountering in production. And last example is to have an example for classification. So this is an image classification use case where we wanted to detect some airplanes. So in red, you have the classification that would be obtained without confidence interval. And in blue, you have a wider detection box with the confidence interval that is provided by MAPIE to ensure we have 90% chances the plane is really located in the location that is indicated. And that's it.
Thank you for the presentation. I have just one comment, is that there is no accident that SpaceX is doing what they are doing the other side of the ocean, and that you are here doing what you are doing. There is a very interesting paper from Edgar Dijkstra, 1982, that says on the fact that the Atlantic Ocean has two sides. North America has a style and methodology of doing things, Europe has others, and you can find this in formal schools and everything that you represent here. So I invite you to read this paper because it explains many things on the choices we do currently. Thank you.